third main type of energy we're looking at is elastic potential energy. You may recall from an earlier video we briefly described what elastic potential energy was. We'll just reproduce that here. So elastic potential energy is energy stored in an elastic object when it has been stretched or compressed. The idea of an elastic object, I just want to touch on that as well. There are two words here that we to be familiar with just to identify the difference between them. So the first being elastic. What we mean by an object being elastic is that it returns to its original shape when the force that is applied to it is removed. So if you stretch something and you remove that force, then it will return to its original shape. The other term that we use that's sort of opposite to that is plastic. And we could just write that it doesn't return to its shape. A better way to describe it is that it will be permanently deformed. And by deformed, we just mean that it's not going to return to its original shape. So permanently deformed when a force is applied. So just be aware of those two terms when we're dealing with elastic objects or things that aren't elastic. So plastic meaning that it doesn't return to its original shape. So you can't store elastic potential energy in a plastic object. If we look specifically at some elastic objects, and those ones that we're going to look at are springs, so specifically designed to store elastic potential energy. They obey Hooke's law, and we'll talk about Hooke's law first because it then makes it much easier to identify how elastic potential energy can be calculated. Now, Hooke's law is basically just that the force required to extend a spring is directly proportional to the extension. So we can write that in a relationship form. And let's finish writing this definition. So the way that we would write that is that F is proportional to the extension of the spring, so delta X being how long the spring has been extended from its rest position. If we turn that into an equation, we then write that as being F is equal to K delta X. And we'll just identify here that F is the force in newtons. Delta X is the extension, or in fact the compression as well. So depending on what type of spring it is, whether it's an extension or compression spring, and that will be measured in meters. Now the value K here, it's a constant term. It's known as the spring constant. And if we have the units of force being in newtons and the units of the extension being in meters, then the units of the spring constant is newtons per meter. The way to think about spring constant is that it's the force required per meter of extension of the spring. And that then leads us to a graph that we can have a look at to do with Hooke's law. And the graph that we would have a look at there is a force versus extension graph. So F on the vertical axis, let me just label this appropriately. So force F measured in newtons on the vertical axis, and extension being delta X on the horizontal axis in meters. So you can see there that it's a directly proportional relationship, and so that means it will have a line that passes through the origin with a constant gradient. So the gradient here will just be the spring constant K. Now, the reason why looking at this first is that the area under that curve in this case it's a force versus I'll write that out in words, a force versus extension graph. And if you think about this situation, the force versus extension graph, what we're really looking at is a force displacement. So the extension here is a distance, so force versus distance. So we've got an Fs graph. That area then is the work done in extending the spring. So we're coming back to that idea of area under an Fs graph. And as we've already seen before as well, if we do work on something, then it gains energy, and so that value is also then equal to so it's also the energy stored in the spring as elastic potential energy. So that then means in this graph, what if we sort of consider this point here where we've got an extension of delta x and a force of F, then this area under the graph here is going to be the work that's done in extending the spring, or the energy that's transferred to it in the form of elastic potential energy. Now you can see in that situation it's the area of a triangle, so the equation that we need to look at here, it's going to be half F times delta x. Another way to think of this half F aspect, imagine instead of dealing with this as a triangle, we simplified it and turned it into a rectangle instead. So if we took, say, this top half of the triangle here and sort of filled in this part here, we'd then have a rectangle that would fit in that area. So the half F value is basically the average of that maximum force. So another way to think of that, why we have this half F term there. As we said though, the work done is also then going to be the energy stored, so we'll use EP here again for a potential energy. Now though, instead of writing F, we can write what F is equal to, which is, as we saw before with Hooke's law, is K times delta x, and we still then multiply by delta x again. And so to simplify that, we have our last version of this equation that you'll note is in the data booklet, half K delta x squared. As I said, that's in the data booklet, so I'll highlight it here. So that equation tells us the energy that's stored in a spring that has been extended, where the spring has a spring constant of K and is extended by the value of delta x.